Now, those of you that's had physics, you probably have heard, and if you haven't, well, you should have. You should be somewhat familiar with projectile motion, okay? Now, of course, they define a projectile. Now, am I going to throw a lot of terminology at you on the exam? Well, I might throw a term or two in there. I mean, you need to understand the vocabulary. You need it. When I say projectile motion, you should know what it means. But more so, you should know what it looks like, okay, physically, all right? I'm more concerned with you conceptually understanding it, being able to look at it and physically understand what's going on than just saying, giving me a textbook definition, because anybody can do that. But if you don't understand what the heck that means, you don't understand the parameters of it, well, a textbook definition is just a textbook definition, and it doesn't really make any sense to you, okay? So anytime you have, and there's a lot of things, y'all, that are projectiles. You know, you can make yourself a projectile. You know, people shoot themselves out of cannons. Well, they become a projectile. You know, if we love to watch football games, well, every time the quarterback throws a football, it becomes a projectile. Same thing for baseball, same thing for tennis, same thing for soccer, basketball. You know, all of our sports actually take advantage of, or manipulate, I should say, projectile motion. Golf is a classic example, okay, of projectile motion. So practically all of our sports are examples of projectile motion. In other words, physical sports that we're actually now sitting at a chessboard. Well, you know, we're not throwing the chess pieces, but you know, they do move, but they don't necessarily move in projectile motion. They move laterally usually, or linearly, horizontally. So, but you know, physical sports, they're all projectile motion, just about it. Anything involving a ball. Okay, all right. So projectiles, of course, they have what? They what you should always remember, that they are always going to be under the effect of gravity, and yes, air resistance does come into play. Now, right now, we're going to neglect it, okay? But, you know, a little later on, we will look at air resistance, all right? Because it does affect a projectile big time, big time. I mean, hit a golf ball. Hit a golf ball and on a windy day and watch what happens. I mean, it doesn't have to be a high wind. Throw a football on a windy day. Kick a soccer ball. You know, even a baseball is affected by the wind. Even though it may be traveling 95, 100 miles an hour, it's still affected by the wind. You know, just to say we can't look at air resistance is that's really not real life physics, okay? But we take one step at a time, all right? So, and it's going to have a curved path. All right, so we see this little diagram here. We launch it with an initial velocity. And these are the parameters of, these are what we call the parameters of projectile motion. Okay, these are what we call motion, M-O-T-I-O-N. Good Lord, it's Monday. Parameters of projectile motion. And what is that? Well, there's always going to have an initial velocity. Now notice it does not have x and y attached to that. All right? It's just VI, period. So what does that mean? Well, we know there's a VI in the x and there's a VI in the y. There has to be. Okay, we're going to look at that in a second. So parameters of projectile motion. Now this is extremely important that you get this right now. Do you see that right there? How in the heck can you miss it? I'm making a mess there. The acceleration in the x direction is always, well, I get in trouble saying always, but right now, neglecting air resistance, okay, is going to be 0. Now notice it says in the x direction. It's always going to be 0. So what does that mean? What does that tell you about velocity in the x direction? If acceleration's 0, what does that tell you about velocity in the x direction? Very good. It's constant. Absolutely. Okay? So, what do we need to remember then? Well, we need to remember that velocity in the x direction is going to be constant. And acceleration in the x direction is always going to be 0. Boy, that right there will make a lot of our problems very easy to solve. Okay? And folks, I'm telling you, you got to. And you say, oh, dear Lord, more stuff to remember. Amen, brother, sister, you got it. Yeah. And if you even want to write it on your formula card, write it on your stinking formula card. Okay, that's fine. Write it on there. That's why you have it, okay? That will help you. It'll help you remember it, okay? All right. But now what is acceleration in the y direction? Now again, these are parameters of projectile motion, okay? So what is it in the y direction? Well, it's always going to be negative g. So acceleration in the y direction is always going to be negative g, which is 9.8 meters per second squared. Okay? Now what about velocity in the y direction? See, they left that on. We got a slide coming up that's also going to show this. Let's go ahead and move to that next slide. Okay. All right. Now here we're not looking at this type of projectile motion from ground to highest point back to the ground. We're just looking at from a high point to a low point. In other words, we're looking at half of the projectile motion. We're just looking at half of it. Does that make sense? Okay. Which is fine. It's still a projectile, and it's still projectile motion. So notice this is still 0, that's still negative g, but what about y? Velocity. Velocity in the y direction, notice it says initial now is going to be what? Just as soon as that ball is released in the y direction, what's it going to be? And we may do this video analysis. We're not having a test this week. We may do this video analysis Wednesday in class to help you understand it. All right, y'all. Initial velocity in the y direction is going to be 0 meters per second. Just as, now do you understand, when I mean initial, I mean just as soon as it comes out of that launcher. I mean just as soon as it's released from the launcher, initial velocity, because it's doing what? It's moving horizontally. Okay? It's moving horizontally. It's not going down yet. Now, you know, a tenth of a second later, it's going to start falling down or less. But as soon as it comes out, initial y is 0. What about final y? Well, that's all going to depend on what? What do you think that's going to depend on? We actually could look at it two different ways. It's going to depend on what? Time or distance. That's right. So final y is going to depend on what? Time, or we're going to say change in y. Can we do that? Okay. Okay. How far does it fall? Or how long does it fall? Will determine final y. And now I'm not talking about when it hits the ground. I mean, come on, y'all. You know when it hits the ground, it's 0. I'm not talking about that. All right. We're talking about just right before it hits the ground. Okay? So final y is going to, and I should say depends on, time or the change in y. Okay? You know, now eventually, y'all, we hadn't gotten to this yet. Eventually, though, an object falling through the air is going to reach what? You physics gurus. It's going to reach what? Do what now? Maximum velocity. That's exactly right. Which is what we call terminal velocity. Okay? And then what happens to acceleration there? There is none. Now that doesn't mean it's not under G. But you got to realize something, that the force of air resistance, now we're looking at air resistance. the force of the air resistance pushing it up is equal to the weight and the force of gravity pulling it downward. And what affects that? Its mass, its shape, okay? Now it's still under G, okay? It's still under G, but it's no longer, it has balanced. The force of gravity has balanced with the force of air resistance pushing it up. And we haven't got to that yet. We'll get to that later, okay? And again, you know, that's why planes, you know, that's why parachutes are huge. When they open up, they're big, old, huge, like a huge teacup. They have a teacup shape. Well, you want a lot of air resistance. Okay, you want to slow down quick, but not too quick. You snap your neck. Okay, but you want to slow down quick enough. You know, you don't want to splatter. Well, I wonder if some of those early people with the parachutes died. I'm sure they did because it didn't work. They didn't pack them right. And I'm going to tell you something, people, today, if you don't pack a parachute right, you'll die. It won't open right. You have to pack it a certain way. You just don't cram it in there. Okay, you have to pack it a certain way or it won't open. And you're dead. You will splatter. Okay. I know that's not pleasant to think about, but you know, if you ever go jump, you better pray to God they knew what they were doing. Okay. Now, I love this slide right here. I love this slide right here because why? Again, we're still talking about parameters of projectile. Y'all, this is so important, and I know it's, but y'all, I'm telling you, this is so important, okay? Because look, all right. Notice how it, and again, please look at your vector arrows. Oh, you know what? I left something off. Y'all should have called my hand on it. We'll talk about it right here, though, because we were talking about a falling object. That was a falling object a minute ago, okay? Going straight down. What about when it's going up? What's the final velocity? Huh? All right, that's right. When it reaches, now notice this is the y vector now. Notice that's y vector here. Let me ask you something. Just as soon as the object is launched, are their velocities necessarily going to be the same? Very good. It depends on what angle it is. That's exactly right. Now, if it was a 45-degree angle, okay, but if it's not, then your y and your x initial velocities are going to be different. We're going to get to how to calculate that. It's real easy. It's trig. It's just, you know, trig function, boom. All right, it's easy. All right, now look. I know y'all shiver when I say he said it's easy and it's always hard when he says that. No, it's not. Okay. All right, get hard out of your mind, okay? Now, look right here. Notice in this direction we only have x velocity. So what happened to y? At the highest point, at the top of the trajectory, notice what it tells us. The final y is 0. So v final in the y at maximum height is 0 meters per second at max height. Y'all, this is another one of those parameters you just need to remember. Okay? It's going to always be that way. All right? Now that's y, not x. X is not going to change. Once it comes out of that barrel, once it comes off, if you're shooting an arrow, if you're throwing a football, baseball, whatever, hitting a golf ball, once it comes off the face of that club, once it comes out of your hand, once it comes out of the barrel, once it comes off the bow, whatever, the x is not going to change. Now remember, we're neglecting air resistance, okay? Right now. It is not going to change. All right? Y'all, I'm telling you, if you'll write this down on your formula card, and remember this, and when you start looking at these problems, you're going to say, oh yeah, x doesn't change. X, that means x acceleration is 0. Boy, when we start looking at those kinematics, boy, it simplifies those kinematics real quick. Okay, because wherever you got an acceleration in the x direction, you put a 0 in. Boy, that simplifies the equations real quick. Okay? All right. All right. Okay. Any questions? Now notice something else. Do you see anything else? And of course they show us here acceleration G's, and that is always there. The y acceleration, once it comes out, is always negative g. Always. From the time it comes out till the time it hits the ground. Always. That is not going to change. Okay. And I know we tell you we don't ever say always and never in physics or science classes. Well, you can sometimes. And here's one of them you can. All right. What else do you notice about this diagram? I love this diagram. Okay. What do you notice about here and right here? It's the same thing, but it's flipped, isn't it? It's negative, isn't it? So what does that tell us about projectile motion? Okay, it's a perfect parabola, which we know in reality it's not because of air resistance, right? But neglecting air resistance, it's a perfect parabola, okay? Meaning what? Meaning that projectile motion has what? Symmetry. It has, that's an R, believe it or not, it has symmetry. Look, at time interval 1, let's just say this is one, let's see, that's x though, isn't it? Y and x, okay. Let's say at this time, because we know there's time elapsing, and I'm going to make this time in that direction. I know it says the x-axis, but we're going to make it a time. It doesn't say time anywhere, does it? Well, I'm going to make it time. All right. All right, now look, at this point and at this point, the same time interval from the center, same time interval, the y velocity, now listen, the y velocity here, yeah, is that y1? Yeah, v1y and v3y are going to be what? They're going to be the same magnitude but opposite in direction. Yes, you're right. No, you're right. You're right. I know what you're saying. Okay? I know what you're saying. So v1y is going to be equal now on this diagram to equal to what? v3y, except one thing. It's negative. Okay? The only difference is that what? v3y is, and I'm going to do this. Does everybody understand that means negative? Do y'all remember that from chemistry? You circle a negative sign, that's a negative charge or a negative value. Maybe I shouldn't do that, okay? Let's just say negative. That make everybody feel better? Is negative. Ah, shoot, come on, right, baby. Is negative, right? So the value is the same, but as far as the magnitude, let me say the magnitude. The magnitude's the same, but the direction is opposite. Okay? So what if that was 15 meters per second at V1? Well, it's going to be what? 15 meters, negative 15 meters per second at V3. Why? Because it is symmetrical. Okay? So then that simplifies things even more. Because we know, let's say, for example, let's say be 1, 2, 3, 4. Let's say this trip was 4 seconds long. Okay? Well, then we know at time 1 second and 3 seconds, our velocities in the y direction are going to be the same, except flip the sign on the third one, on the last one, at time 3. Make it negative. Boom. I don't even need a calculation. I don't need to calculate that. Don't need to calculate it. And again, why is that the case? Well, let's see, folks. The slope at that point is going to be what? Negative. Right? Absolutely. It has to be. Okay, any questions on that? Okay? Projectile motion is what I meant to say. Has symmetry. Okay? Now, we're good? All right. And it should have said that somewhere on this slide, but it doesn't, so I said it. Okay? All right. These are good slides. Okay. So, now, how do we determine initial velocity in the x and the y? Well, it's really simple, y'all. To determine, let me back up a slide. To determine initial velocity, VI, in the x, all we do is we take our initial velocity and say cosine. Now, y'all, why do they use alpha? Every math class I've ever had, and even on most physics classes I've ever had, always uses theta. They use alpha. Do you want me to use alpha just to keep everybody happy? Theta, alpha, I don't care what Greek letter you use, just angle. All right, just angle. All right. I don't know why they use alpha. Keep it theta. I've always used theta. We've always used it, even in trig and physics and everything. So to find the initial velocity in the x direction, it's initial velocity times cosine alpha, or theta. Well, duh. What about it in the y? Well, it's the same thing except sine. Okay? All right. And that's it. So listen, you've got to listen to these problems when you read them. If it says, we fired a cannon at the communist, whatever, we're in war, heaven forbid. We fired a cannon, fired 105 artillery at our enemies. I'll just say our enemies. I won't pick anybody out, okay, because they might be our friends one day. Who knows? All right. We fire our 105 artillery at our enemies with an initial velocity of, 75 meters per second at an angle of 30 degrees to the horizon. Well, that's how the question's going to sound. Okay? What will be the maximum height of the projectile? Okay? And some of y'all already know, hey, that's our calculus equation, maximum height calculus equation we learned from Mr. Leith. Yeah, you're exactly right. You can use that one or another one of our kinematics. You can still use the kinematics, okay? You just got to find, first of all, the initial velocity in the x direction if we're wanting to know, what's the maximum height? Not in the x, but in the y, because remember, that's y, right? Maximum height. So what's the maximum height? Well, that's y, isn't it? Okay, so you can use your max height equation from calculus, and we're going to get to this. A little later on, we're going to talk about range. You can use your range equation, or you can use the kinematic. Either way. Okay? All right. And I don't care which one you use. Just make sure you do it right. All right. Okay? And by that, I mean you got to remember when I say it's launched at an angle of 30 degrees to the horizontal at 75 meters per second, that's not x or that's not y. That's initial. And you got to find x and you got to find y. You follow me? Okay. We'll work some problems. You'll see what I'm talking about. All right, now, so guess what happens to our kinematics? Well, come on, y'all. They're going to change a little bit. But look, y'all, these are the same stinking kinematics. They're the same kinematics. The only thing we did is do what? We stuck in cosine and sine. They're the same kinematics. Okay? Nothing has really changed. All right? Look at this one right here. That is this equation right here. Look, y'all. V final is equal to what? V initial plus what? AT. Except instead of doing AT, they did negative GT. And they stuck in a sign because it's in the Y direction. Huh? Look at this one. That's just to find the initial velocity. Look at this one right here. Come on, y'all. You better recognize that one. All right. Now, where's the initial Y, Mr. Shields? Well, if we're starting right here, all right, look. We got a cannon. We got a piece of artillery. And let's go big, 155. Yeah, bless God. Let's do some damage. Or what's up next up? 200 or 210 millimeter? I forgot. All right, look. When that projectile comes out of that barrel, boom. Okay. Well, what's initial? Yeah, okay. What's initial? I can't draw. All right. What's initial? What's initial Y? 0. Okay, we don't need it. That's why it's not there. So I don't want you to, and some of y'all probably already figured that out, but I just want to make sure. When you look at these equations, don't flip out. Just think a little bit. Say, oh yeah, it's starting at ground level. Well, Y is 0. It's starting at 0. Okay? All right. And look right here. Well, which one is that? Well, y'all, come on now. Okay? Yeah. All right. So guess what? There's you some more equations to put on your formula card. Really and truly, y'all, do I need to write them down? Well, if you feel better, yeah, but really what you should be able to do, and again, I'm not trying to scold anybody or make you feel bad, because I know some of this is Greek to some of you. I understand that. That's okay. But I want you to think a little bit and look at what's going on. Well, all they did is took the kinematics and put in sine and put in cosine. That's all they did, okay? That's all they did. And if it's in the y, they did negative gt, or negative 1/2 gt squared, because it's in the y. Okay? And remember I told you can still do plus, just remember to make g negative. Okay? And I think I've preached that till I'm about ready to, my eyes are about ready to pop out. I think you know that by now. Okay, right? Okay, everybody good with that? All right, now look, here's another good slide showing the reality of air resistance. So it's really not a true parabola, a perfect parabola. Boy, look at the difference on a baseball's velocity. Now you think about an outfielder standing out there at 325 feet, 350, and he can throw somebody out at home plate. Are you kidding me? But there are guys out there in the majors that can do it. Can throw people out at home plate. I've seen videos. Man, I mean, now buddy, that's hurling us baseball. And the thing about it is, the dude is taking into account air, you got to think if it's a windy day, the wind just swirls in those stadiums. So, he has to think about that when he throws that ball. So that's crazy. Throwing a ball, not many can do it, but there are a few that can throw them out at home plate. I forget who it was several years ago. They showed a guy, and he caught a ball, and he threw the dude out at home plate from it was over 300 feet out in the outfield. It was crazy, y'all. It was crazy. He's a big old guy, too, man. And, he took that thing and out. So, yeah. Okay. All right. What about motion in a circle? I do want to go ahead and cover this. Now, notice it says uniform circular motion. Uniform circular motion. Now, one thing about uniform circular motion is that you will have, now please write this down, constant speed. Okay? All right, now, well, if we have constant speed, Mr. Shields, we cannot have acceleration. Wrong-o. Okay? Because with uniform circular motion, notice it says that our acceleration is at a what? Acceleration is at a right angle to what? To velocity, or the car, the direction of the car. You're right. Okay. All right. It's at a right angle. Okay, so the acceleration is perpendicular to the velocity vector. And notice these are vectors. All right. Now, but how do you have acceleration with constant velocity? All right, well, the reason we have acceleration with constant velocity is this right here. Car is changing direction. So, what does this mean? Uniform, let's sum it up, uniform circular motion. Okay? Uniform circular motion. All right? It's when we have constant speed okay? And the acceleration vector is perpendicular to the velocity vector. Okay? And the reason we have acceleration, now you say, well, wait a minute, we've got constant speed, but it accelerates due to change in direction. So that is how we have acceleration. Okay? So you got changing direction. All right. So here is one exception to what I've been telling you. Well, if you got constant speed, you don't have acceleration. Well, you do if you're going in a circle. How do you think they accelerate? The NASCARs do what they do. Okay? When they hit those bank curves, man, they pick up speed. I mean, they're already running, what, 180, 190? Okay? Maybe a little faster than that. And then they hit those bank curves, and, man, they accelerate. They accelerate some. Because, you know, you got to realize something. They all know the tricks of the trade as far as the engine. They know how to build an engine. And you can only build those engines so much. I mean, there's rules and guidelines by that, so they all know that. Okay? And, you know, there are certain things you can do maybe to get a half a horsepower there and a half a horsepower here and there, but in reality, they all know the tricks of the trade. Okay? So how do you win the race? Okay? Knowing how to maneuver through those curves. And where are most of the wrecks most of the time? In those stinking curves, aren't they? When they start going into those curves. Okay? Because they know when they hit that bank, they're going to accelerate. It's physics. Okay? And so they want to take advantage of that. Okay? All right. And how much somebody's paid somebody else to let you win. Who knows? I don't know if they do. You know, I sound like Speed Racer, don't I? It's, you know, they've already got it fixed, right? You know, it's fixed. And not for Speed Racer. He beat them all. All right, now. I love that movie. Anyway. So y'all are deprived. You didn't grow up watching Speed Racer. See, when I was a kid, I watched every one of those cartoons, and they were great. But anyway, Chim Chim and Trixie and all of them, it was great. All right, now. Okay. Okay? All right. So just think about Chim Chim hanging on that seat. All right, now, okay? All right. So how do we solve for uniform acceleration? Well, again, we can look at it as a derivative, okay? And notice how we take average velocity and take the derivative of velocity with respect to time. And notice how they plug in here. Notice how they plug in, they say delta S. Well, then why did they do that? Because it's changing direction, not changing velocity. And so with that, we actually, what they did is what? Took the what? They didn't take a derivative, because derivatives you do what? You subtract. So they actually did what? They had to integrate here, didn't they? Okay, did they do an integral? Looks like they may have done an integral. I know that's a limit, but if you take the derivative with respect to time, okay, you got to come up with a v squared, okay? All right, so now here's another equation right here. Boom. Okay? So if we want to find uniform acceleration, notice it says radial. Okay? Notice it says radial, not tangential. And there's a difference, and we'll look at that. It is what? The velocity squared divided by, now notice they use a capital R, the radius of its path, circular path, okay? So please remember that, okay? So there, and please write it down this way. Please write it down and label it magnitude of acceleration of an object in uniform circular motion, and that is the key. Uniform circular motion, not non-uniform. In other words, changing speed. All right. Any questions? All right. Now, what about, of course, what does this lead into? It actually leads into what? Centripetal acceleration. All right. Because why? Well, because when you look at radial acceleration, radially, what is that? You have what is called a center-seeking acceleration. So in other words, the acceleration is towards the center. So the acceleration is what? Center-seeking. Okay? So we call a center-seeking acceleration centripetal. That's what it's called. Now, I know they labeled it RAD. Well, why? Because of it's radially accelerating. In other words, it's accelerating towards the center. And across the center is the radius. Okay, radially. Okay. I'm not talking about tangential. We're not talking about out here. Not yet. Okay, not talking about tangential acceleration. All right. All right. And define the period for the time of revolution. Notice if we take our equation here, notice it says the period is the time for one revolution. Well, if we take that into consideration, all right, okay, and we use a little bit of what? A little bit of trig here. All right, we know that this is what? Pi. All the way around is what? 2 pi. Okay? So, we can do a little bit of manipulation, and I think this, I don't know if they show you how they manipulate this equation or not. Let me look right here. I'm on page, yeah. We can find the velocity. Let me write this equation. Uh-oh. Let me write this equation. I'm sorry, page 84. This is on page 84. On page 84, we can find the velocity of an object going in a circle with this equation right here. Okay, now why, whoa, wait a minute. How in the world did you do that, Ms. Shields? Okay, y'all, think about it. What is a circle? Geometrically, trigonometrically, it's 2 pi, isn't it? Okay. Well, now, wait a minute. That's 2 pi radians. Is radian a legit... Now, boy, I got to be real careful saying this, because I said this one time, and people, boy, some of the students looked at me like I was nuts. Okay, and I understand. But is it... Okay, let me ask you this. Let me ask you this way. Do you have a radian ruler anywhere? Have you ever gone to the store and bought a ruler in radians? I've never used one. We measure in what? Meters. Now, I'm not saying radians are not real. Of course they're real. We do it all the time. But remember, radians is related to degrees of arc, right? They're related. But you don't buy a radian ruler. We don't measure in radians physically. We don't go out here and say, okay, let's get the radian ruler out. Boop, there's not one. Okay, we measure in degrees, and we measure in what? We measure in meters. Okay, so we take our radius times 2 pi, because that really ties back into what? Well, the circumference of a circle is what? Pi times diameter, or pi times radius squared, right? Okay, that really kind of ties back into, it similarly ties back into the circumference. Okay, we're going in a circle. So, a complete circle is 2 pi. Okay, in order to determine the depth of the circle, we got to throw in the radius. Okay? Now look, we got to have a time interval in here too. Because what is velocity? Y'all, it's got to come out meters per second. You're not going to get meters from radians. You're not going to get meters from radians, but you will if you multiply times radius. Okay? So 2 pi times the depth of that circle from the center, depth from the center, radius, divided by the time interval it takes. And now, boy, here's where we get confused. What is the difference between period and frequency? Boy, we got to be careful with this one. Period is the time for what? The time it takes to complete what? One cycle, one revolution, right? One. Frequency, now be careful, is the number of cycles in 1 second. It's the reciprocal of period. Huh? I've asked this, I've done this before on tests. I've asked this and people get it backwards. Now let's think about it. How long does it take to go one cycle? One cycle, that's your period. But how many cycles do you have in 1 second? For example, the RPMs of your motor. That's frequency. Revolutions per minute. They just do it in minutes instead of seconds. How many times does it complete a cycle in 1 minute? Okay? That's frequency. You with me? Some of y'all look at me like I'm crazy. All right? Think about it. So please don't confuse period. I understand it's a little, but listen, don't confuse the two. All right? So now look, when we take this and plug it in, look, we square velocity. Look, we square it. And so now we can find the centripetal acceleration by using what? The radius. In other words, look, if we don't know the velocity, y'all, we can find it if we know the radius and we know the period. So here's another nice little equation. So let me erase all this cuneiform and hieroglyphics and whatever else you want to call it. So please write that equation, and please remember this equation too. The velocity, and this is for circular motion, 4 pi squared. No, I can't believe I just did that. I just turned right around and did something stupid. Okay, my bad. 2 pi r over what? T. Okay? So there's you two more equations. This is what? That is centripetal or radial acceleration. You can call them both. And this is velocity for circular motion. God, I cannot talk. Circular motion. Okay? So please add that into your formula card. Okay? Because that formula is not on here, but it's in your book. And that was what? Page 84. Page 84. Okay? Everybody good? Okay, now relative velocity, just a couple of things I want to say about that. I'm not going to spend a whole lot of time there, and then we are done with the chapter. Okay, all right, and again, notice this is a nice little diagram, again, just showing you how notice how each vector is the same. Okay, again, projectile motion, showing the symmetry there. What about non-uniform? Well, non-uniform, notice it says the radial component is still this, but we have what is called tangential acceleration. That is what? That is parallel to the instantaneous velocity, okay? So in other words, what does this mean? Okay. Tangential, now remember I mentioned that a minute ago. So we have what? We have radial acceleration, which is also known as acceleration. If I write it AC, do you know what I'm talking about? Centripetal acceleration. Okay. Tangential, however, is parallel to the instantaneous velocity. So we do what? We take the derivative, remember? We take the derivative to find the instantaneous velocity, and then do what? Divide it by the time interval, right? Yeah. Okay. We can do it that way. So you actually can have differing accelerations when it's non-uniform circular motion. If the motion is like speeding up, slowing down, speeding up, slowing down, speeding up, slowing down, okay? Okay. Everybody good? All right, now, yeah, maybe, right? I hope not. Okay. And I know we work some problems and they'll help. All right. Now, what about relative velocity? Okay. The biggest thing with relative velocity is this right here. Remember, how do we define relative velocity? All right. Relative velocity is how it is seen by the observer. Okay? In other words, I'm standing by the 4-lane. Okay? And I'm watching cars pass me. All right? Well, it all depends on where I'm at and where the car is relative to me at a given time interval. For example, if I see a car coming relative to me, it may just barely be moving when I first witness the motion. It just may look like it's just barely moving. And I'm talking about, I don't mean like standing literally right beside the 4-lane. I'm back, say, I don't know, 50 yards, 25 yards. And I see the car. Well, it may look like it's just barely moving at time 0. But as it begins to approach me, I'm going to notice that the velocity changes. Okay? So relative to me, the car may go from what may appear to be a very low velocity to its regular velocity. However, the car, to me, is going to be the same thing. He's going to be looking at me, and he's going to see me and say, hey, look at that dude out there by the 4-lane. What's that crazy nut doing? You know? All right, and he sees me standing there. And he's just looking at us, just standing there. Well, I'm going to appear motionless to start with. But as he approaches me, I'm going to do what in his background? I'm going to move, right? I'm going to move against his background. This is where, have you ever noticed if you're sat beside a car or truck or something, especially in real heavy traffic, and stuff's moving, it feels like you're moving, but you're not? You ever felt that way? Ever get that motion? You kind of get motion sickness? You'll be sitting there, and especially if there's cars and buses, like on a subway, or if you're in a real congested town and there's a big bus or big trucks right beside you, and you're sitting still, but they're moving this way, and you feel like you're moving when you're not. Okay, that's relative velocity. Okay, and things appear to be moving, and you even feel like you're moving, but you're really not. Okay, so it all depends on what? The frame of reference. And here again, y'all, what comes into play? Okay, what comes into play? All right. The most important thing that comes into play, of course, first of all, is your initial velocities and your position. Okay. Now on page 89, and I think this is in our, let's just skip that slide. Okay, yeah. They talk about, notice this right, we extend relative to 2 or 3 dimensions by using a vector addition. Now notice, again, the train is doing what? All right, the train is moving this way. The boy's sitting here still. Okay. All right. Notice the passenger looks like they're moving 1 meter per second. Okay. So how fast is the passenger going to appear to moving compared to the boy? Then we could turn it right around and say, well, how fast is the boy going to be moving compared to the passenger? Okay. So you can turn it around either way. What we're going to end up doing is creating a bunch of right triangles. Now, and again, if you want to write this equation down, you can. But what it winds up being is a combination, or it's the addition, it's the vector addition of all velocities. Okay? Now notice we have, and if you look, like I said, page 89 is a really good sample problem. And maybe we work, well, I don't know if we'll work one today, but we will later, where we have an airplane flying and the wind's blowing it. The wind's, you got a crosswind. You're flying directly straight, but you wind up over here to the northeast of where you were headed. Okay. Well, there's a difference in your actual velocity and your relative velocity. Okay, because that direction changes it. Okay. All right. Now, end of the show. So if we look at that, and I know some of you have a book, some of you don't, page 89, and we'll try to work a problem like that on page 89, just so you can kind of get an idea of how to calculate it. But basically what you end up doing is you end up taking the square root of the squares, okay? Okay? To find your overall velocity. That's what it winds up becoming because it's a right triangle. What you wind up with is a right triangle. Okay? Okay. Okay? And direction means everything. Remember your axis. This would be positive x. What if it was this way? Well, this is negative x. So when I did the square root of my squares, then you're going to have to do what? Subtract them out. Okay? If you're doing it for that problem right there, because notice you're in the negative x quadrant here. You got to subtract them out and then take the square root. And we'll try to do a problem later on where you can see what I'm talking about, okay? But it becomes, like I said, it's vector addition. You take the square root of the squares, and then guess what? To find direction, it's arctangent. Okay? It's not hard.